Hello everyone, my name is Edwin Guerra. I am a BIM specialist and engineering designer in the Vancouver office of Associated Engineering. This is stream 3.2, HVAC and electrical. A reminder that you can ask questions and favorite them. We will address those questions at the end of each presentation. Please do make sure to use the question section and not the chat. I will remind you of that using the chat. We will have two presentations today. Our first speaker is Azad Khamforoush. Azad is a mechanical engineer in Associated's Toronto office. He has over 14 years of experience in design and implementation of HVAC, plumbing, piping, ducting, and building automation systems for municipal, industrial, commercial, multi-residential, and institutional projects. He brings experience from projects in Canada, Iran, and other countries in the Middle East. He also plays guitar, sings, and this is his first professional presentation delivered in English. Azad, the floor is yours.
Thank you, Edwin. Can everybody see my screen?
Looks good, Azad.
Yes.
Okay. Hi everyone, and thanks a lot for joining us in this session. As my colleague Edwin mentioned, I'm going to talk about the design and retrofit of HVAC system in the age of COVID-19. Many of us heard a lot today during the panel discussion, whole lots of discussions about resilience and how engineers should factor that in their design. On this specific presentation, I'm going to basically talk about some of those strategies that we can implement into our building mechanical system to basically make for a better and more resilient buildings, and that could basically be more prepared for, God forbid, next pandemic. So at the beginning of this presentation, I will provide some brief information regarding SARS-CoV-2, which is the virus behind this COVID-19 pandemic, and how it travels through the air. After that, I will discuss basically some HVAC strategies, including filtration, ventilation, pollution control, humidity control, and some other technologies out there that we can be implemented into design in order to remove those infectious droplets that are the major cause for basically getting people sick or making people sick. At the end of my presentation, I will touch base on the position of some of those regulatory bodies and standards like CDC and ASHRAE Epidemic Task Force, and provide a list of the recommendations that so far they have come up with. SARS-CoV-2, as many of you may know, is the virus behind this COVID-19 disease. These particles of coronary viruses are basically spherical particles, and they do have a size between 0.06 micron to 0.14 micron, with an average size of like 0.12 microns. Just to give you some better idea about the size, here on the left, we do have a single coronavirus with the size of 0.1 micron, compared to other particles, some of them like some bacteria, blood cells, and PM2.5, that you can get some sort of idea. On the right side, droplets containing this virus are shown compared to human body hairs. So just for your information, that droplet is already 35 times larger than a single virus. So that's basically for you to know what we're talking about when I refer to size of the virus. There are different modes of transition, as many of you know by now. Direct person-to-person interaction or close contact is one of the major ones. There are other ways that people can get sick, including indirect contact with infected objects and stuff like that. Also, airborne virus particles known as aerosols. This is the major focus of basically this presentation, as I'm going to introduce some ways that we can prevent these aerosols from spreading in the indoor environment. So airborne transition, according to CDC, is defined as a spread of an infectious agent caused by the distribution of those droplets that we are going to call them aerosols moving forward, and remain infectious and suspended in air over long distances. So bioaerosols, as I showed in my previous slides, you'll usually have somewhere around 5 microns when it comes to their size, and they contain viruses. So airborne transmission of viruses can occur through them. So the typical size is between 0.3 to 5 microns, and they can stay airborne and potentially travel through HVAC systems, which is make them very, very dangerous and very problematic. They are typically much larger than individual virus particles, this is the fact that is a key to stop their propagation. Now, in my future slides, I'm going to discuss how we can remove these bioaerosols from our indoor air using different HVAC strategies and HVAC systems. The first means of removing these bioaerosols is via filtration. We can remove these bioaerosols from the air through the use of filters, and the efficiency of that filter, the higher the percentage of bioaerosols basically removal. So true that this COVID-19 situation and this virus is quite new, but in the past, human has faced many other different issues, including influenza. And from the past experiences and the studies that is out there, we know that, for instance, MERV-7 filters can achieve 42% average removal efficiency, while MERV-13 filters achieve basically about 86% of removal efficiency in a typical HVAC system. So for those of you who don't know what MERV is basically an abbreviation for Minimum Efficiency Reporting Value, which is a measurement scale designed in 1987 by ASHRAE to report the effectiveness of air filter. So in many commercial systems, as you may know, MERV-13 is pretty much a standard filter that many designers use in their designs. Now, I mentioned that filtration can be helpful when it comes to removal of the bioaerosols. Another method for removal is ventilation. We can remove these aerosols from indoor air through air exchanges, which is to say by diluting the indoor air with outside air. Now, the rate of bioaerosols dilution is correlated with the percentage of outside air relative to the recirculated air. For an example here, as an example, with 15% outside air, you can remove about 15% of the bioaerosols, and while by doubling that number up to 30%, that removal percentage is going to be only 19.5%. So a very important note here that these rates are based on the ASHRAE 62.1 ventilation rate procedures, which is based on liter per second per square meter and liter per second per person. So for the designers, that's an important notification. Now, I spoke about filtration and ventilation and their impacts on removal of the bioaerosols. However, here we want to try and basically compare the two methods that so far we discussed. On this chart, you will see two different scenarios for outside air, three different scenarios, for outside air, starting from 5% outside air all the way to 19.5%, and with two different types of filtration. As you can see, in any strategy with MERV-13 filters, approximately we can achieve 90% removal, which is great. So this tells us that proper filtration is a much more effective way at removing bioaerosols from indoor air compared to outside air ventilation. Now, multiple studies have confirmed the superiority of filtration over increased ventilation in reducing the transition risk of airborne viruses. Right? So no surprise that relative risk of contracting COVID-19 in a commercial building has more to do with filtration strategies than with ventilation strategies. So this relative risk can be determined quantitatively using a tool called Wells-Reilly equation. Now, this equation was developed in the 1970s, and it is the most common approach so far for assessing risk of infection to humans in buildings by taking into account parameters such as the size of the building, number of the people in the building, number of infected people, and the amount of time that infected people spent in that building. We can basically calculate NC, or what is called a predicted number of new cases infected over a period of time in seconds. So I'm not going through the equation. There are so many parameters but for those of you who are interested to know more about this equation, please reach out to me at the end of this presentation, maybe in one of the rooms, so we can talk more. Now, this relative risk infection, as I said, can be calculated. So we, for different filtration and outside ventilation scenarios, try to apply this equation over basically a typical building with somewhere around 100,000 square feet, which is equivalent to now 9,290 meter or square meter. This building is considered to be occupied by 1,000 people, and among those, 7 are infected. So we want to see, using different scenarios for filtration and outside air ventilation, how much the relative risk of infection will be. So the left side, that VRP black bar, shows us the method, or basically the ventilation rate procedure that so far, I would say 99% of the designs we follow based on ASHRAE 62.1. As you can see, for different types of filters, there are different risk of infection. To start with the HEPA filter, that number is around 8%, while for MERV13, which is a pretty standard filter, nothing so fancy, you will see numbers around 9%. Now, by increasing the outside air all the way to the right, somewhere around basically 100% outside air, is where all the filters show the same, basically a risk reduction. This is not have anything to do with the filters. This is more to do with the fact that we are pretty much replacing the entire inside air with outside air. This is not something that we can do in many applications, as you know, for different reasons. So this chart again shows us that with improved filtration, the benefits of increasing ventilation are more or less minimal. Pollution control and why it matters. I heard over from the other meetings that there were so many concerns raised about these wildfires. We know that recent studies show a link between pollution and both the spread and impact of respiratory viruses on people who are infected. A recent Harvard study shows a small increase in long-term exposure to particulate matter size 2.5 micron leads to a large increase in the COVID-19 death rate. Why? The reason is pollutants inflame lungs, potentially making catching the virus more likely and its impact more serious. Now, several studies also show particles of pollution might carry the virus, which can facilitate its spread. In Italy, a correlation between elevated concentration of particulate matters and the high spread and mortality rate of SARS-CoV-2 was found. So based on these studies, building owners and HVAC engineers should consider pollution levels before increasing outside air ventilation, as a higher intake of particulate matter could facilitate the spread of viruses and make building occupants more susceptible to the impacts of virus. The smaller the air, the more problematic they can be. We know that airborne pathogens can travel up to around 25 feet from a sneeze. We know that it's not difficult to imagine that larger, heavier droplets tend to travel only a few feet from an infected person. But based on their size and the environment, they can remain in the air for up to 2 days. So on the right side, chart from AHRI that shows how different particles floating time is varied. So for particles that are larger, it could take seconds for them to settle. For particles anywhere smaller than 3 microns, it could take hours for them to settle, and that could be problematic. Now, I'm talking about the size of the particles, but how aerosol size changes. We know that there is a connection between the humidity level and the aerosol size. And that brings me to the next slide. Basically, in dry air, and by dry I mean relative humidities under 40%, the moisture in droplets evaporate quickly. However, the droplets don't go away. They just get smaller and smaller and remain airborne for longer periods and traveling greater distances, which is unfortunate. These smaller droplets or particles not only last longer and travel further, they become more lethal, as they can be inhaled more deeply into the lungs. So basically, many viruses and bacteria are drought resistant and have increased viability in low RH or relative humidity conditions, right? We know that relative humidity has an impact on immune system. In fact, immunobiologists have now clarified the mechanisms through which ambient RH below 40% impairs mucous membrane barriers and other steps in immune system protection. Very bad. Many studies also shown that relative humidity of 40 to 60% inhibits the spread of viruses. Now, how we know that? We know that coronavirus is something relatively new, but there is a fact that Sterling chart that was published in 1986, basically they've done so many different research on different particles, including viruses, and for this fact, they used influenza viruses. And they showed that infectiousness of the virus increased as the relative humidity decreased below 40%, but it increased again when the relative humidity went above 60%. This is a very famous chart for the HVAC folks, but the big takeaway from this chart is that relative humidity near 50% is probably the best overall. But please be cautious and do not take that chart basically literally, right? People can still get sick or have allergic reactions even at 50% relative humidity. In addition, and as you can see on the chart, the risk doesn't change linearly. Now, so far I have been able to touch base on 4 different strategies, including filtration, outside air ventilation, pollution control, and humidity control. But let's talk about other measures that we can implement into our designs or into the building mechanical system to help with the removal of these problematic bioaerosols. The first technology is bipolar ionization, which uses a precise electronic charge to create an electrical field filled with high concentration of ions, positives and negatives. So this ionizers helps in 2 ways. The first way is basically these ions travel through the air and they seek out and attach to the particles. By attaching themselves to those particles, they make them more larger and basically heavier. And these larger, heavier particles are easily captured by the ventilation and filtration system, or maybe they become too heavy to remain suspended in the air. I use maybe because based on the size of the aerosols, it could be different scenarios that will happen with bipolar ionizers. The second way that these bipolar ionizers can help is when these ions are injected into the air stream, they also break down pollutant and gases into harmless compounds. So that sounds like a kind of interesting fact, but how? The way these ions are helping is basically they come to contact with harmful pathogens like viruses and bacteria. Whenever that happens, they steal away their H2 molecules. H2 means energy. Without H2, pathogens are left with no energy source to carry on, and they apparently die. Now, there is a problem with these ionizers, or potentially there could be a problem with them, and that's the potential, they can potentially create ozones, which we know is not good for indoor climates. For an ionizer to be considered safe and used by an HVAC engineer, they must not develop any detectable ozones. So third-party testing shall confirm ozone levels less than 0.00 ppm. So that means if we get 0.003 ppm, our ionizers pass that threshold. However, if we get 0.005 ppm, basically that's no good. This is great, right? Shall we use them? We can use them. However, apart from ozone creation risk, the time that it takes for an ionizer to disinfect to certain levels is long. According to the test that has been done by manufacturers and not the basically independent third parties, it takes approximately 60 minutes to achieve average reduction of 90% in viral titer using a commercialized ionizer to disinfect that basically titer. So here is where another technology comes to help, which is Uvc lights. We know that ultraviolet light mangles the genetic material in pathogens. For example, RNA in coronavirus, and this preventing them from reproducing. On that little photo, bottom of my slide, you will see an RNA. And for those of you who are not sure about what is RNA, RNA is basically a molecule that holds the virus's genetic code. So by mingling with that, we prevent that virus from reproducing itself. And that's a key, basically, to stop them from reproduction. These equipments are called ultraviolet germacidal irradiation, and they employ a wavelength of lights known as UVC that are shorter than UVA and UVB. The shorter the wavelengths mean that photons are of higher energy. So it is proven that wavelengths band killed or inactivate microorganisms, but people have been told for decades to wear sunscreen to ward off skin cancer caused by these UV rays. There is an important notification there that those harmful UV rays are called UVA and UVB with much higher wavelengths. What we are talking about here is UVC, which can be absorbed by the sun in the atmosphere. So that's why we don't have any of that in a sunshine day. So we have to create them artificially. That's why certain manufacturers has developed an equipment similar to what you see here, which is a combination of a ionizer and UVC lights. And basically, we know, I already mentioned that UVC is safer for people as it is absorbed by the proteins in the outer layer of dead skin. I didn't mention that, but because of that higher energy or basically lower wavelengths, they will be absorbed by the dead skin cells before reaching the DNA in a living cell. So they can still irritate skin and eyes, and that's why UVC sterilization lamp installed in the return air boxes to kill those bacteria entering to that unit and or maybe absorbed by the filter. So we know the short length of 200 to 275 nanometer can deliver a sterilization rate of around 99.9% when unit is running, and that is great. But let's see what's regulatory body's position when it comes to these technologies. CDC, or Center for Disease Control and Prevention, has already recommends using portable high-efficiency air filtration systems for the safe reopening of schools and office buildings. They also recommend including UVGI, or ultraviolet germacidal irradiations, as a supplemental technique to inactivate potential airborne viruses of common occupied spaces. As a matter of fact, they've already approved UVGIs as an addition to filtration for reduction of tuberculosis risk, and that guideline has been published back in 2005. So this is nothing new. We're just trying to use some of those existing technologies to deal with the this pandemic. This was about CDC. However, we have a long list of recommendations provided by ASHRAE, which is American Society of Heating, Refrigeration and Air Conditioning Engineers. ASHRAE recommends to increase the outside air ventilation by opening the outside air dampers 100%. Now, I am not 100% agree with that recommendation because we simply explain that leaving outside air damper 100% is not a viable option for all applications. We may need to remember the discussion that we had earlier regarding the pollution and its impact on virus spread and mortality rates. So that's I would take that recommendation with lots of salt and pepper. Also, they recommend to improve central air and other HVAC filtrations to MERV 13 or the highest level practically basically achievable. So we realize that using the MERV 13, we can reduce the risk all the way to 10% risk of infections, which is great. It's better than not having anything. Also, they recommend to keep the systems running for longer hours, 24/7, and add portable room air cleaners with HEPA or high MERV filters with due consideration to the clean air delivery rate. And
we are at the 26-minute mark.
Sure. And they also add UVGI devices to the HVAC systems and where applicable, and use those HEPA systems to protect against this SARS-CoV-2 virus in a high-density commercial and institutional systems. They recommend maintaining the temperature and humidity, as we discussed about the humidity earlier, and the temperature has a lot to do with comfort levels. They recommend to bypass energy recovery ventilation systems that could potentially leak those contaminated exhaust air back into the outside air supply. And whenever possible, they ask for incorporation of local exhaust or source capture ventilation for source control. For instance, 100% exhaust of patient rooms are required, or healthcare buildings, when it comes to the building mechanical system, must exhaust toilets and bedpans and deliver clean air to their caregivers. They also recommend to increase the air exchange rates from 2 to 6. This is different than increasing the outside air. This is basically to get more air exchange, therefore there will be more chances to capture those viruses or droplets via filtration system. And also, wherever possible, maintain that rooms with infectious aerosols concerns at negative pressure. As you can see, ASHRAE does not include bipolar ionization in their position paper, probably because unlike UVCs, there has not been sufficient testing done by credible third party on ionizers for ASHRAE to conclude one way or another. So all the claims we have seen so far are from the manufacturers and based on their own test procedures. However, it's known that ionization works well when it comes to removing or reducing volatile organic compounds, particulates, and pathogens in indoor air. From this, we can conclude that it will have a good impact on most airborne virus pathogens as well. However, we still need to wait for more tests to be done before finding out what will be ASHRAE's final position on those. With that, I will conclude my presentation, and back to you, Edwin, in case folks have any questions.
Yes, thank you, Azad. We'll run quickly through at least a couple of questions. One here says, what are your thoughts on the use of operable windows as a means for dilution or mitigation of the virus?
It's basically depends which building or what kind of application we are talking about. Overall speaking, I do not recommend that, because by opening up a window, we will lose our control over the humidity levels. And also there is a chance for some of those particulate matters that could potentially carry on viruses to come inside that building. So no opening windows except you are quite sure that you are living in a suburb neighborhood with not basically riskful situations that you can expose your indoor air quality to it.
Thank you. We'll do one more. Is there a good instrument to measure the existence of these particles in the air or the filter?
In fact, different companies now, they have implemented an IAQP method that is also adopted by ASHRAE 62.1. They can come and take samples from the indoor air and do some measurements. It's a very, very on its early stages, but yes, it can be measured. As a matter of fact, many large cities like Toronto, they will keep measuring those things in their basically weather stations. But I'm not sure if they are sharing those data on a daily basis with their city occupants. So it's very important that pollution control is another thing that maybe caused lots of folks in downtown Toronto to move out to suburb areas. But I'm not suggesting that everybody has to do that, but it's just important. And yes, there are ways to measure those, but it's not basically there is no sensors, as far as I know, that can do that measurement or provide that measurement continuously.
Sure. I recognize that there's a few more questions. I will encourage you to, when we actually have a break, to create a networking room where you can hopefully join Azad and discuss some of these.
Sure.
But thank you very much for that presentation.
Yeah. Thanks a lot, everyone, for participating, and yeah, have fun.
Okay. So we'll begin the next presentation in the stream presented by Scott Friel. Scott started his career at the Canadian Standards Association in the Hazardous Location Department. He worked briefly in New Mexico in the United States and in the oil and gas sector in Alberta before joining Associate Engineering's Edmonton office 18 years ago. An electrical specialist, Scott has varied design and construction experience, specializing in ETAP, harmonic mitigation, lighting, and troubleshooting. Furthermore, you may be surprised to know that his deft floral arrangements have earned him fame in botany circles. Scott, the floor is now yours. And I think you're muted.
There we go.
There. Perfect.
So here we're here to talk about the replacement of electrical equipment. In particular, the key is the 1980 stimulus funding that occurred. A lot of projects were completed, water, wastewater, buildings projects, a lot of funding occurred, and that equipment is now 40 years old, and it's working, so no one seems to be complaining. The key with all this money is that it's now 40 years old, and it's now time to replace a lot of it, and not a lot of people are worried about it. So first, before we sort of get started here, I want to talk about some of the definitions that IEEE Gold Book uses. The availability of power is a common term in utility provision of power. If you have high availability, the lights are always on. If you don't have high availability, the lights are off. And the key here is the stated period of time, which is the mean time to failure, which is another discussion. So the lights are on. I'm a little ahead of my presentation here. I'll pause. So after availability is reliability, which is the ability of a piece of equipment to work when you expect it to work. So a reliable piece of equipment will work when you want it to, and availability is a combination of all the reliability in your system. So if you have a well-maintained site, dry, clean environment, you vacuum out your equipment or wipe it down once in a while, you make sure there's humidity control, you're going to have a reliable equipment. After you combine all of your reliable equipment, you can then calculate your available equipment. I'm not going to show you how to do that. What I can show you is for a site where we did calculate it. Now, when you're looking at this chart, remember, this doesn't mean that this year, this site, because it's 40 years old, is going to have a 20% chance of failure. Statistics has no memory. It's going to still think that it's new. But if we were to install a piece of equipment today and look at 40 years in the future, you're probably looking at 15 to 20% of that equipment will have a failure of some sort. So again, you can't look at this chart and say a 40-year-old piece of equipment that has a 20% chance of failure this year, but rather any equipment that we install today will most likely, 1 in 5 will have a failure within 40 years. The key takeaway is the longer the piece of equipment is in service, the greater the chance of failure is going to be, and you sort of have to plan for that, and that's the point of this presentation. So when you're talking about availability and reliability, there's something called the rule of 5 nines. So 599.999 is basically 5 minutes brownouts or blackouts per year. That is pretty good. Not a lot of people would be very happy with 5 minutes of brownouts or blackouts, but at least it's tolerable. Usually in Edmonton during the summer, we'll have a brownout or blackout during a high air conditioning event, usually a hot summer day in August or possibly July. 99% is terrible because that means you've got 3 days to 4 days a year where you don't have power. Associated Engineering, we've actually designed systems with a lot of nines, and I haven't even counted those nines. And yes, we can design main systems with this kind of availability if we have 2 utility power feeds. can be done. You can ask questions about that later on. But not a lot of facilities are going to have a main time main, so they will suffer from a single point of failure. You might remember that from the resiliency presentation earlier. Louis had mentioned that we forget that that transformer is a single point of failure at the front of the plant. If that transformer does happen to fail, the whole site goes down, and it will take days or months to replace it. So the takeaway message here is we need reliable components. You've got to maintain them, you got to keep an eye on them, and make sure that they're working properly. So this is a picture of a transformer that is only 20 years old. This is the ground lug at the bottom of the transformer. Notice the powdered rust collecting on top of the ground lug. This transformer is working, it's happy, it seems to be a little bit warm, but it's also piling up rust on a day-to-day basis because of the amount of corrosion. This is a thermite weld in a hospital. It was installed 3 years ago. It's in a parking lot where they use calcium chloride and other salts to keep the ice down, and the thermite weld is all but separated, so we've got a little bit left there. But it hasn't given us a problem yet. So why do we worry about all these things? Electric components, they look small, they're pretty inert, there's not a lot of moving parts, but once you look inside the electrical equipment, you'll find that there's a lot of metal and a lot of plastic. And it's that metal and plastic and the fatigue that becomes the problem. This is a standard household breaker, and these are all the little parts to it that make sure that it's going to protect you, your family, and your house. Now the key strip here is there's something called a Biometallic thermal overload protection. There's the springs, and then there's the short circuit coil. So the two things that are going to fail here are that bimetallic strip and that spring. If either of those components get relaxed or fatigued in their position, they're not going to work as intended. They're not going to suddenly fail. They're not going to suddenly release. They might, but they're not going to work when you want them to. So if you look at one arena, you might have 6 panels across it. Each panel could have between 12 and 84 circuits, so you're looking at about 500 circuit breakers. And later I'm going to tell you that it's about 1 in 20 of those circuit breakers aren't going to work after 30 years. So that means you're going to have 25 circuit breakers in this arena that is 30, 40 years old that aren't going to work when you need them to. So if they're not going to work, now you have to look at repairs and downtime. So you've got your availability, you've got your reliability. Now let's take a look at what's going to happen when these breakers don't do what they're supposed to do. So if it works until the next time it trips, you might find that it cannot be closed or reset. Now that's fine, sure, no one got hurt, but unfortunately you can't turn the lights back on. This typically happens with more expensive breakers, so your main breakers. So if something does happen, you trip the main breaker, you go to return it, and it doesn't go back into its normal state, and it just stays off. If you manually open it because of maintenance, you just can't close it again, no matter how much you try and lock it back into place. Now, these types of repairs, you typically can get somebody to come to site and repair it within 24 hours. It's usually mechanical repair. Now, you can have death, injury, and building damage. I'm not a big one to immediately jump to death, injury, and whatnot, but this is a case where you can have it. You take that same exact circuit breaker that we just discussed. It's supposed to trip, but it stays closed. So when it stays closed, that fault that's occurring is going to overheat and eventually start a fire. This is typically something that happens in homes where you drive a nail into a wall, you have a little capacitive fault through the nail, eventually the system gets hot, it's supposed to overload, but it doesn't because it's just so small. It's not enough to actually trip your breaker. It'll eventually start a fire. Now, let's say you've got a breaker, it's supposed to trip and it stays closed, and someone's holding on to those wires for whatever reason. They have a toaster, a kettle, or they're working on a lighting circuit in a building. And that's when somebody gets electrocuted. So again, if you have a circuit breaker that is supposed to open, but it doesn't, and someone's touching it, they're going to get electrocuted. And last but not least, if you have an arc flash, which is basically a little chunk of wire on top of a breaker when it trips, you could have arc flash, which is a combination of fire and injury. So the key here is we want to keep your lights on and safely. So again, we want to have available power with reliable components, and we want to do it so that your people and you are safe. So when should you be doing these types of repairs? Now, I brought up the 1980 stimulus money because that's 40 years. Circuit breakers will last reliably up to about 30 years, and then 5% won't work. Eaton's got a white paper on it, Schneider's got a white paper on it, but effectively, if you've got a small building with, say, 500 breakers, you're looking at, 25 of them probably won't work when you want them or need them to. Transformers, Louis brought this up in the previous presentation. He mentioned 50 years. That's a fairly constant number. They will last a lot longer than that. There's no moving parts. If it's a clean, dry environment, you can get a transformer that lasts for upwards of even, 75, 100 years, depending on a lot of the factors around it. But again, 50 years is a nice reliable point before transformers start to get aged. Now, cables and bus bars can last up to about 100 years reliably. Now, where do we get this data? Because there's not a lot of cables from 100 years ago that we use the same technology today. This is based on IEEE data, where they've collected all this data from industrial sites. So they've got some pretty good approximations. They don't know, but I think if you install a wire in the 1980s, you probably will get about 100 years out of it. Bus bar, as long as it's not corroded, should last about 100 years. Now, Schneider says they've got 15 to 30-year serviceable life. That means they've got shelf and store components that are available to be maintained and replace whatever's there. So after 30 years, they might not be storing the components. I sort of chuckle at this one because copper's copper. If I've got a 4-inch piece of 3/4 thick copper, it's copper. So I can always do some repairs there. Now, if you have a site, I would start to plan and engineer at about 30 years. Now, no one's going to actually do that. Your budget's not going to allow it. Everyone's going to be worried about operating costs. They'll be worried about ventilation, COVID-19, and trying to keep the facility running. But if you start planning for it at year 30, you're probably going to be okay. Then once you've got your plan done, you're going to budget to do it at 35 because you're going to have to convince everybody that to give you the money to do the repairs. And let's be perfectly honest, you're not going to get it done right away, and hopefully you'll have it done by year 40. If you don't have it done by year 40, you're still going to be generally okay. Hopefully most of your faults will be minor. But again, if you start planning at 30, you're in pretty good shape. Budget for it at year 35, but try and complete your repairs by that year 40, if not 45 or 50. A lot of my clients are pushing it off because, well, budget. So how do we do these types of replacements? If you have a transformer, it's at the front of the plant. It's going to power everything. So when we do replacements of major equipment, it's going to take down your whole facility. So an electrician or 2 electricians can do a standard panel in about a day. So that means isolating it, taking the power down, so the lights will be off, the computers will be off, HVAC equipment will be off. But they will be able to go in, look at the panel, take out the guts, replace all the wires, clean everything up, relabel it, and put it all back together in about a day. Some guys will be able to do it a lot faster if there's a smaller panel or if it's all the wires are long enough and everything's nice and clean. But usually I account for about a day for every panel. So typically most electricians will have multiple teams. So when they take down an area after a transformer, they'll do all the panels connected to that transformer. And that way they minimize the downtime. And as well, I don't ask them to do it on the weekend or evenings. Now MCCs and switchgear are a little bit more complicated. You can do a single draw breaker rebuild in a morning. However, whatever is connected to that switchgear substation is going to be down. So no matter how you cut it, you're looking at days. Doesn't necessarily have to be consecutive, doesn't have to be all in a row, but you're going to have multiple shutdowns that are going to take days and typically about 4 hours per cell. And if you look at a small chunk of switchgear as maybe 6 cells, you're looking at least 3, maybe 4 days. So expect shutdowns, lots of them. But again, if you've got the planning done, you can do it without too many issues. Now, a lot of people say, well, I'll just use a generator. Right? Well, that's you totally can use a generator to provide power. Now, the only problem with you have generators, this is a hospital job we'll discuss later, it takes time to disconnect all the cables that are connected to that piece of equipment. Then it's going to take time to connect all those cables from the generator to that piece of equipment. And then you have to turn on and make sure everything's working right, the rotation's correct, fix all the little surge protectors in the buildings that popped because someone did something wrong. So now you've got your generator running. Well, that, let's say 4 to 8 hours of disconnecting, connecting cables, because there's a lot of cables, you could have just done the work. Now, granted, if it's a small job that takes less than, say, 4 hours, well, why even use a generator? Just do the work. Don't worry about the generator. If it's a site that usually has it, needs a generator, it takes a lot of time to connect those cables. So at the hospital, what we did was we connected the cables. We did the work because it took about 8 to 12 hours, and then we disconnected it again. But again, we were down 2 to 3 hours to disconnect the cables and to connect the cables at the front and back of that task. So we do need to schedule an outage. We do have to take the stuff down. And the key here is planning and figuring out what is the correct order to do it in. And sometimes generators are the right choice, sometimes they're not. Now, MCCs and switchgears, we typically use a generator or another feed. Again, if we go back to some of the discussions I said earlier about those 5 nines, if we have a system that is a main time main, we can provide power without having the generator connected. So we can actually backfeed and find clever ways of feeding the facility to provide power. So generator might be the right choice, probably not for a panel. The key here is if you design your facility right, your MCC and switchgear, you could probably backfeed and find some clever ways of figuring your loads. One thing I usually find electrical engineers do incorrectly is we put all of our loads on one side of the bus. And when we do that, it's hard to backfeed if all of our backwater pumps or all of our fans are on the right-hand side of the bus and we have to take down that side. If we put half of our loads on each half of the bus, then we can always have an opportunity to provide power. So I mentioned earlier the Misericordia Hospital. So what we're looking here is some 50 to 60-year-old outdoor rated gear on the far left. Yes, this is outdoor rated gear. There's an outside door that's open. There's the switchgear inside. It's a big fuse disconnect, and the relaying's on the opposite side of the system with the contactor. In the middle is the cables. Now, this was the nice feature. So what we did was we designed the new substation building, which is on the right-hand side of this photograph. We built everything. We fed cables into this tunnel that's in the middle. So all we had to do was cut, splice, and test those cables, and we're back up and running. So while the hospital was running on backup power, we were able to, we already pulled in all the cables, we cut, spliced, and moved on. So because we had space, we were able to rebuild the entire electrical system, sit it beside the old electrical system, run cables, and then cut and splice, and we were up and running without many problems, actually. It didn't hit the news, so therefore it was a fantastic job. Now, this other one was very complicated because the original breakers didn't fit the bus bar. So we had to modify all the bus bars. Now, some of you will look at that ground bus and immediately say massive corrosion, and you'd be correct. So we had to lubricate and clean the bus bar connections for the breakers. We didn't clean all the bus bars. We didn't have time, but we had to get back into that switchgear to measure. And then after we measured, the guys went off, basically built all the copper extensions and splices. We came back a couple months later with all the breakers, with all the bus bars, and we basically had a shutdown on a Tuesday, on a Wednesday, and then the week after. We could only shut down the plant for 4 to 6 hours at a time because a process upset beyond that would cause too much ammonia and cause a lot of problems. So we had to break these shutdowns. Do we use a generator? No. What we actually used was a temporary power panel. So we actually took a lot of these feeds, took it to a temporary switchgear. We fed it from the other half of the substation. I should have actually shown some single line diagrams, but I figured a lot of people wouldn't be interested in looking at the single line diagrams. The electricals after this, we could chat about this and I can share my screen and show you guys what the single line diagram looked like. We did add some neutral CTs as well to pick up any kind of imbalances and faults and sped up the protection. So is an electrical upgrade for you? Well, yes. If it's critical infrastructure, you should have a main time main, keep up your maintenance, and pretty much you're good as long as your building was, built after year 2000. So again, critical infrastructure, you probably have a main time main, keep up on your maintenance. And if it's older than 2000, you should start planning. You've got lots of time, you've got about 10 years. But if it's built after 2000, well, you've got even more time. So if it's back at 2000 or 1980, I would definitely start thinking about it now because some of those breakers aren't going to work. Non-critical infrastructure. Now, your initial design was probably had a need to be affordable. So I'm going to bump this back and say, was it built before 1990? If it was built before 1990, yeah, I'd start looking at a plan. After 1990, you probably have some time. But remember, be prepared for a complete shutdown. Might be for a week of shutdowns, could be weekends and evenings, but either way, you're going to have a lot of shutdowns. Regardless if it's critical or non-critical, keep up on your maintenance. That'll buy you a lot of time. So associated engineering, we can do arc flash studies, which is Z462. We can do maintenance plans, which is Z463, and we can help assess the condition as well as make the plans for shutdowns, replacements, and budget recommendations. While I have your ears, lighting is something that's usually forgotten. And You should be cleaning it every 2 years, and no one does. You should be replacing lamps if they're not LED every 5 years. No one does. And you should be replacing ballasts every 8 years, which again, no one does. And because you don't do any of these things, everything's quite dim. And then someone comes along and says, hey, let's throw some LEDs in there, and that you find that the room is twice as bright. Well, that's because your existing system had old lamps, old ballasts, and they were dirty. LEDs do provide a little bit of a maintenance relax. You should still clean them every couple of years. However, you do have 10, if they're cheap, and 20 years before you have to replace them. So that's a little bit of pro bono lighting work there for you. So our goal here is to make sure that the lights are still on safely, and we can help you do that. Any questions?
Yes. Thank you, Scott. We have a few questions. First one here is, have we approached clients with putting together an upgrade plan that they can apply for funding or save money on? Cheap starting point that I have had good luck with in the automation world.
Yes, I've been hired several times to provide studies, assessments, and budget plans. They're all 5 to 10 years behind schedule. Not me, the client and budget. It's they've always put money someplace else. So we have, like right now, I'm working on one for EPCOR for some substations. I work a lot for Alberta Capital Region for substations. The City of St. Albert, I've been doing some. But yes, I have been paid to do assessments, planning, budget, and recommendations.
Great. We have another question. I have seen MCC starters where the components are not available in a time of about 10 to 15 years. Does that sound right?
Starters. Yeah, if you have MCC starters where the components are not available in 10 to 15 years, I'd recommend sticking to the major vendors. GE is no longer what I would consider a major vendor, but if you've got Schneider and Eaton, I have Schneider replacing Magnums that are 30 years old with the same exact frame. Sorry, Eaton with Magnums with the same exact frame. And there's some other Schneider ones that I'm replacing that have the exact frame still. So they haven't changed. The technology, the breaker changed, the relays changed, but the guts are identical. So if something is obsolete at 10 to 15 years, I'd change vendors. It probably was just a cheap buy up front, and maybe they bought some stuff that was on the discount rack.
I see. Another question. In the presence of chlorine, as you would find on a water treatment plant, equipment will last less than the figures you have quoted. PVC has chlorine as a component. I have found plant corroded where off-gassing of chlorine or SHF has occurred. Have you experienced this?
Thank you, Derek. Yes, chlorine will attack everything. Correct. If your environment is poor, if your ventilation is poor, and your maintenance is poor, then your equipment will degrade very quickly. That one transformer that I was showing you that was less than 20 years old was Chlorine Attack. And literally the case and a lot of the copper is turned to powder. So yes, chlorine is worse than H2S, but H2S is still pretty bad. But yes, if you have chlorine or sodium hypochlorite or another kind of off-gassing chlorine type, it will destroy your electrical system very quickly.
Great. Another question here is, how do your clients do on maintenance?
I've only been hired a couple times to do maintenance plans for them, but the larger the company, the more they have their own maintenance staff, electricians, and instrumentation techs. They're the ones that are kind of interested in this. If the client doesn't have any maintenance staff, typically all the electrical goes by the wayside until it's an absolute failure, and then it sort of talks about what Louis, the transformer fails. They've got 30 weeks out of with no power, so they have to bring in temporary generators and alternative power. So if a client does have maintenance staff, they usually do provide a decent facility. They listen and they try and keep things well maintained. If they don't have maintenance staff, like a common commercial building, usually that goes straight to the failure of the equipment before they actually get it fixed, and then they never actually replace it. They just sort of bandage it and move on. So bigger the client, the better to work with, because they have the foresight to save money and not have that downtime.
Yes. We have another question or comment. Some items would have different lifespans, such as lights and VFDs.
Lights hopefully are going to be LED now, which will be in the 20-year range. The life there, as well as capacitors, coincidentally, are both on the dependency of the capacitors inside the VFDs and the LED lights. If you buy a cheap VFD, it might only last 10 years, even less. Buy a cheap LED light, it might only last 3 or 4 years, maybe 10. If you buy a better VFD, name brand, as well as lights, you probably will get 20 years out of a light. VFD is another good question, because if you would ask me 15, 20 years ago, I figured 5 to 8 years was a good life out of a VFD. But I've been to sites where I've installed them back in 2006 and they're running just happily after 14, 15 years. So a lot of VFDs now, because of that sort of infant mortality that they had early on, late 90s, early 2000s, they've corrected those mistakes. And you can get a good solid 20 years out of a VFD. Again, per Derek's conversation, if you've got clean, dry air, if it's cool, and you maintain it. If you don't clean those fans, because those little filters that fit in the front of the VFD, and they got all clogged with dust, your VFD is going to overheat. You're going to impact the life of it.
Thank you, Scott. And are you able to comment on instrumentation? And is that a weakest link, or is it comparable to other pieces of equipment?
Instrumentation, that's a good question. I haven't really thought about that for this presentation. I don't know, is Chris Brado? I don't know if he can unmute himself or if someone else is there, but I don't have really a comment on instrumentation, how that would compare. I will flip it around. If you do have instrumentation and control, most people replace their cell phones 3 times before they should replace a PLC at a plant. The plant affects the whole community's health, whereas your cell phone is for personal convenience. So I would say people don't replace instrumentation as often as they should. They don't replace their control system or modernize it as often as they should. Yes, it's industrial hardened electrical equipment, but everyone seems pretty keen on their cell phone and not worried about their plant.
Yes. We have one last question. Have you included ROI calculations in your pricing, showing the difference between maintenance, plant replacement, and field replacement, including operational costs?
Interesting question. Only for lighting. We've done that actually for the city of Peterborough, Ontario, and we actually calculated the cost and the savings of actually just doing pre-planned maintenance to replace lights instead of waiting for one to fail. Now, inside of a plant, typically most people that want to maintain their plants want to do it before they have a failure or shutdown. So, for example, if you're an Alberta Environment reportee and your facility has a unregistered discharge of untreated effluent, it's $1 million fine. If I'm selling clothes in a store and the lights go out, I just can't use my till. So there's $1 million fine for a moment of failure versus I can't sell whatever product I'm selling until I get power back in my building. So a lot of people aren't motivated to actually provide that kind of maintenance plan or the return on investment, but the people that would have the money to calculate the return on investment already know that it's there. So again, very few people would ask you for the return on investment because the people that don't have the money to pay for it won't lose money, and the people that would lose money were probably going to be fined or have a significant cost impact. So but we could do that calculation quite easily. If Suncor and Syncrude called me up and said, can you do to calculate use the IEEE gold book, determine the rate of return, the cost of the shutdown. It's all in the gold book. It's really quite complete. They've got approximate mean time down, mean time to repair, and you can calculate all those returns. But again, most people that have the money to pay for a return on investment investigation already know that maintenance is important. And the people that don't have the money don't care.
Thank you, Scott. We have another comment from Chris Brado. Instrumentation controller replacement schedule depends on the item and service widely. Yes.
And then Jared followed up with computers 5 years, 10 years for HMIs, 15 years for PLCs, and he recommends instrument is replaced with the PLC at 15 years. Not a lot of people do that, but again, people seem more concerned about just keeping the operation and maintenance costs low, because it's a pretty big bill to go in and replace instruments, even though it's a good idea. Instrumentation also, the flip side of that, they probably are calibrating it. Most sensitive pieces of equipment are calibrated regularly. If I had an HVAC system that had dissolved oxygen, or all the equipment that Azad was just mentioning, a lot of that equipment does require calibrations. And if it's not kept up, they will drift, and then your system starts to fail. So instrumentation does get a lot of inadvertent maintenance as well as replacement to keep things working properly.
Excellent. Well, with that, I encourage all of you to create a networking session in this break that we will be starting. And thank you to both of our presenters, Azad, Scott. Thank you for your time. We will regroup again for session 4 in 30 minutes. Again, the networking happens in the virtual lobby at the very bottom. Be sure to join. Thank you again, and goodbye.
Thank you, Edwin. Thank you, everybody. Thank you, Spot.